All right, so this is going to be the recording for Chapter 7's Stats Study Guide. And so this is going to be on making confidence intervals for both estimating a population percentage or proportion, a deviation, or a mean. So the first few questions here on the study guide are simply asking you to find critical values. So remember, critical values are those z-scores, t-scores, or chi-scores that basically set the boundaries of your estimate. So these are the values that you get to figure out how far up and down your estimate's going to go, and that you will ultimately convert into an e-value later on. But in this case, we just want the critical values themselves. So number one here says you're going to be using a 99% confidence level, excuse me, a 99% confidence level, and for a population average, your n is 41 and you have an unknown standard deviation. So if you do not know your standard deviation, or it should say you don't know it's an unknown population deviation, it should be a little bit more clear there. But since you don't know your standard deviation and you have to use your sample deviation, that means you're going to be left with doing a t-score. Again, the only reason you'd use a z-score for a population average is if you knew the population deviation to begin with, which is that little sigma there, which in this case it says we don't because it has an unknown standard deviation, so we don't know. So we're going to look up a t-score on a t-score chart, obviously. We're going to have a 99% confidence, so 99% confidence level, which implies that we have a 0.01 alpha level. Well, let me try it again. So we have a 0.01 is our alpha. That's our percent of uncertainty. And then our n is 41, so our degrees of freedom is going to be 40. So remember, degrees of freedom is simply one less than the number of numbers you have. So if we take a look at our chart here, our t-score chart, we have 40 degrees of freedom right here. And we have 0.01 as our alpha. Remember, we're using the area and two tails because we could be wrong either on the low or the high end. We're setting the boundaries for my estimate. So the boundaries are going to be both low and high. And we check down here and we get 2.704. So that's for 40 degrees of freedom and a 0.01 alpha, or 99% confidence. 2.704. 2.704. And that's all we need for this problem. It's not asking us to find the E, it's not asking us to find the interval, it's just asking us to find the critical value for the situation. And that t-score right there represents the critical value. It says find both critical values for a 95% confidence interval of a population deviation estimate with n equals 13. So we're estimating a population deviation, right? That's what we're trying to figure out. We're trying to estimate. So that means that we're going to be looking up a chi-squared. So a chi-squared, remember, is this little symbol right here. There you go. That's just kind of that's the critical value table, critical value values that you use to estimate population deviation. And the keyword here is also that you're going to find both, because this is the only one where you actually have to figure out both, because everything else is symmetric. Like this technically is plus or minus 2.704. And z-scores are also like that, plus or minus. But chi-scores are not symmetric, so you actually have to look up both manually. So what you do is you take your confidence level, 0.95, 95%, and you split it into your unconfidence, 0.05. Okay, so you take your confidence level, make it into your unconfidence level, or at least get your unconfidence level from that, your uncertainty level, and then divide it by 2, and you get 0.025. Now, this is only one end of your chi-square. Remember, we want to find both the low and the high end critical value. So 0.025, that's my low end value. My other high end value is going to be 1 minus 0.025, which gives you 0.975. So these are going to be the, try that again. These are going to be the two values you're going to look up in your chi-square table to figure out what your critical values are, what your chi-scores are. Excuse me, I had a hiccup there. So, again, in order to find the critical value components for this table here, you first take your confidence level, you get your unconfidence level out of that, so it's just the other version of your confidence, 1 minus your confidence. And then you divide that by 2, so this is your uncertainty level divided by 2. And then you subtract it from 1, and you have two values you want to look up, the one that you did when you divided by 2, and the one that you got after you subtracted from 1. Because again, it's not symmetric, so you have to kind of manually look for both. So we're going to go to our chi-square table. So we're looking for 97.5 is our first one right here, right? So this is the third row over. And we had, I forget, n is 13, so our degrees of freedom is going to be 14. So 14 degrees of freedom right there. And going that way, there we go. So we look here and say, okay, my first critical value is going to be 5.629. That's going to be the critical value for my chi-squared there. Hold on. Oh, my bad. I almost made a mistake and had to redo this entire video. So my degrees of freedom are actually going to be 13, or sorry, not 14. It's going to be 12 because 13 minus 1 is 12, not 14. I accidentally added one there. I am kind of tired right now, so that might be the reason why. So we're going to look at the 12 there. There we go. Almost made a major error there. So 4.404 is my target chi-squared for the 0.97 column, right? 0.975. So for the right end of the spectrum, essentially, 4.404. Look at that here. 4.404. And then for the other part of my chi-squared, I'm going to look up 0.025. So here is 0.025 right there. Look down to the 12th degree of freedom. You get 23.337. So 23.337. And those are your two critical values, right? So again, chi-squareds take a little bit more time because you have to look up both manually, but overall it's still just reading a table. You do have to do a little bit of work ahead of time, a little bit of prep, but after that, it shouldn't be that big of a deal. Just make sure you don't mess up like I did and make sure your degrees of freedom are one less than your n, not one more. Number 3 says 78% confidence for a population proportion. Now, for a population proportion, we use a z-score, right? So population proportion is always a z-score, and normally we have predetermined values for z-scores of 90, or sorry, for the z-scores for a 90, 95, and 99 confidence level, right? We have those already given to us in the table. However, this wants a 78%, which is a little bit unusual, but we can do it. So we take our 78%, kind of like we did with the chi-squared, and we make a uncertainty level out of it. So for 78% certain, that means we're going to be 22% uncertain, right? This is my alpha, essentially. That's my uncertainty level, is 22%. So then, just like with chi-squared, you're going to divide this by 2, because your z-score table only shows 1/2 of this. So divide it by 2, and you get 0.11. And you go to your z-score table, and you look up 0.11. So you're going to try to get as close to 0.11 in the middle here as possible. That's the idea. So where is close to 0.11 as I can get? Here is 0.1112, so that's getting pretty close there. Let's keep looking here. Actually, you know what? Here's 0.1093. That might be the closest I can get here. Actually, I think doing some little mental math here, this one looks to be a little bit closer. So this one would be the one that I would go with because it's a little bit closer to 0.11 than the other one. So it'd be negative 1.203. So negative 1.23. That would be my ultimate critical value for that case. So that would lead to a z-score of negative 1.23. There we go. And again, the reason actually it'd be plus or minus because remember z-scores are symmetric, unlike chi-squared. So I can just look this up and be done with it. So it's going to be plus or minus 1.23. But again, I get that simply from the left-hand column here, negative 1.2, and then I go to my target value and then go up, and I get 0.03. So negative 1.2, 0.3. That's how I got my answer. 82% confidence interval for a population average with a known standard deviation. So if you know the standard deviation, we're going to assume that means of the population. Then you can use a z-score for this as well. So you can use z-scores for population averages as long as you know the standard deviation. So 82% confident, that would leave me with a 0.18 alpha, 1/8 unconfidence, which when divided by 2, that gives me 0.09. And again, just to save you some trouble, if you look this up in the table, you end up getting negative 1.34. Or at least that's the closest I found that I could get. If we check that here real quick, negative 1.34, we should get as close to 0.09 as possible. So negative 1.30, 1, 2, 3, 4. Yep, that's about as close to 0.09 as I think I can get there. So that would be my critical value. Again, it would technically be plus or minus, but again, that's all right if you just write within the table. So, all right, so that's finding critical values. Again, you're just simply looking them up in the table. They're probably going to take the largest chunk of your time when you're doing those word problems. But again, once you get them looked up, it's no big deal. Number 5 is kind of a working backwards problem. So number 5 says that you have somebody who's estimating the percent of students who stream themselves playing video games, and they get this interval. what's the statistician's sample proportion and margin of error? So sample proportion is p hat. That's kind of what they got from their sample, and margin of error is their MOE or their capital E, however you want to say it. Their, like I said, their margin of error, their regression range. So to get the p hat, what you do is pretty straightforward. To get the p hat, you simply add your two values together and then divide by 2. Basically find the middle of them. So this comes out to be 0.38, and that would be his population average. So of the people he surveyed, 38% of them streamed themselves playing video games, and that's how he made his interval there. That's his best single guess. To get the margin of error, you do much the same thing, except that instead of adding them, you're going to subtract them. 0.42 minus 0.34 divided by 2, and that will get you 0.04. So again, nothing too major there. As long as you remember to add to get to p hat and subtract to get to e, we should be fine. Because again, p hat literally is the middle of your interval, because the best possible guess you can make is the average middle of the interval, and then your margin of error tells you how much leeway you gave yourself in the extremes. All right. So 6 here says that we have a study commissioned by Uber to find the number of hours people spend driving a car. We want a 90% confidence, and we want a margin of error of no more than 0.75, and we're going to assume that the deviation for the hours that people spend driving is 1.8 based on past studies. What will the sample size be? So I want to figure out what n is. So there's a formula for this for population average. N is equal to your z-score, or your t-score, times your sigma over your e squared. And so in this case, if it's 90% confident, my z-score would be 1.64, because that's the 90% confidence trick there. That's what's given for a 90% confidence. And then we have a sigma of 1.8 and an e of 0.75 and then squared. And so again, you would type all this math in, and you would get 5 point, I think it's like 26, which you always round up to 6, right? That has to be your sample size if you want to have a 90% confidence with a margin of error of no more than 0.75. Again, it seems kind of small, but that's because the numbers I chose made it that way. Um, so again, there's nothing really tricky here. You just have to kind of remember the arrangements of your items here. Because like I said, it's really just a matter of making sure that, making sure that, like I said, you pay attention to what numbers you have here, because there's going to be a word problem. There's going to be lots of stuff going on. So make sure you pick out the right stuff, right? Second here, give me a second. There's another way you can look at this here too. You can say that it's basically like this. The E formula for this is E equals Z sigma over root n, right? And so if we solve this for n, we should get back to here. Now I'm thinking I made a mistake here, which is why I'm doing this, but let's see what happens. So we're going to multiply both sides by root n, right? So if we multiply both sides by root n, we get root n e equals z sigma, and then we divide by e, so we get root n is equal to z sigma over e, and then we square both sides, and so we get z sigma over e squared is n. So I made a mistake up here. My square should actually be over the entire thing, not just over the e. So it actually should look like this. 1.645 times 1.8 over 0.75, and then this entire thing is squared. That's what I get for, like I said, doing this when I'm tired. So 1.645, come on, 1.645 times 1.8 divided by 0.75 and then squared, we get 16. So not much better, but still a little bit better than 6, I guess. So 15.5, we round up to 16. So 16 people would be our sample size there. So again, that was my mistake there. And so thankfully I caught it before I submitted the video. Otherwise, I'd have a bunch of people telling me I'm wrong, which is no different than normal, right? Anyway, that's how you do. So again, ignore this formula right here. This was the formula that we should be looking at. And again, as always, you should check your work as well by, if you have time, solving it yourself and making sure that everything's on the up and up. Now let's see if we can do this one without any errors here. We've got 2 errors so far. Hopefully we can get no more. The desired margin of error for a study, to study a percentage, is no more than 10%. We want a confidence interval of 95%, and there's no prior data on the subject. What would the sample size need to be? So this formula, once again, the base formula is this. E equals, for a percentage, it's Z times root P hat Q hat over N. So if we solve this through, we should get something along the lines of N equals Z squared times P hat times Q hat over E squared. And I'm pretty sure that I got that one right. So that one I'm pretty sure that I'm correct on. And now it says here that we have no prior data though, so we have no idea of knowing what P hat and Q hat are. So in that case, if we have no idea, just want to do a voice check there. If we have no idea about knowing what P hat and Q hat are, we're going to assume that they're both 0.5 because this is going to give us the widest possible margin of error. And again, we want to assume the worst if we don't have any prior information. So we want to give ourselves the widest room for error because again, we don't know what we're starting with. So we have 1.96, which is the z-score for a 95% confidence level. We have 0.5 times 0.5, which is 0.25, if you're wondering, all over our margin of error, which is no more than 10%. So 0.1, which is 10% as a decimal, squared. And I should probably square this too. Almost made another mistake there. So once again, your E is not 10, it's not 1, it's 0.1 squared. So just make sure we're careful with that. Let's see here. So if we calculate this out here, 1.96 squared times 0.5, whoops, let's try that again. Answer times 0.5 times 0.5, and then divided by 0.1 squared. We end up with 96.04. So again, we're going to round that up, and we're going to say that it's approximately 97. Right? Again, you always round up when you're estimating a sample size. So again, these formulas are similar. This formula right here for a proportion and this formula right here for an average. But just again, make sure you know which realm you're dealing with. Are you dealing with the population average estimate that you want, or are you dealing with a population proportion estimate you want? Because that's going to determine which formula you use, even though they both use Z. All right, so these are the more wordy problems here. This is kind of like one of each type of confidence interval we made, right? So the IQ scores of 35 people who take a stats class in college is recorded. The average is found to be 120, and the deviation of the sample, which is important here, is 4. If the study group wants to create a 99% confidence interval for the IQ scores of people who took a stats class, what will the interview be, or what will the interval be? All right, so we want to make a 99% confidence. Let's record our information here. 99% confidence, which leads us to a 0.01 alpha. We have so that's our CL. We have an N of, let's see here, 35, right? N of 35. We have a standard deviation of the sample, so that's a little s, of 4, because that's a sample deviation, not a population deviation. And we have an average of 120, so our x bar is 120. Again, I just find it helpful to list out all my information first, rather than just kind of jumping right into it. So my formula, which again, I'll give you your formulas, but my formula for this is going to be E equals, since I'm dealing with a standard deviation of a sample, it's going to be T times S over root N. So let's plug our numbers in here. E equals my t-score. Once again, I'm going to look up 0.01, and then I'm going to have 34 degrees of freedom. So if I go to my little table here, 0.01, so first column, 34 degrees of freedom right there. So that'd be 2.728 would be my t-score, right? Again, 0.01 degrees of freedom, 0.01 is my alpha, 34 degrees of freedom. They cross right here at 2.728. So 2.728, and then my z-score is 4, or sorry, my sample deviation is 4, and my n value is 35, because I have 35 people that were a part of this study or whatever. So I multiply all that junk together, and I believe I get 1.84, right, if my algebra holds true. And so my final answer would be 120 plus or minus 1.84. And again, you can physically do the plus or minus on the 120 if you so choose, but I would just leave it like this. So again, that's our confidence interval there. Again, nothing too major from the first few problems we did. It's just basically tying them together. So we haven't really done anything too nasty with them yet. Just make sure you know your E formula, make sure you can pick the one that's appropriate in each situation, and you should be good to go. Number 9 here says the average credit score of 61 people in a certain state is found to be 620 with a deviation of 25. Construct a 95% confidence interval to estimate the standard deviation of the population. So we want to estimate the standard deviation. We want to estimate sigma. So if we're going to do that, that calls for a chi-squared score. Let me try that again. There we go. Chi-squared score. So in order to get a chi-square, well, let me again just list out my information here. So 95% confident means I'm 0.05 as my alpha. I have an n of 61, so 61 is n. My average is 620. And then my current standard deviation that I got from my sample is 25. And again, the reason I know that that's weird. Let me try that again. 620 is equal to x bar. There we go. The reason I know that this is the sample deviation is because I'm trying to estimate the standard deviation of the population. So if it says a deviation of 25 and I'm trying to estimate the standard deviation of the population, I know that this is not it. Otherwise, I wouldn't need to be estimating. I'd have it. So it's good. That 25 there is the sample deviation, even though it's not directly said. So to get a chi-squared, what we do is we take our alpha, 0.05, we cut in half, and we get 0.025. And that's going to be our first lookup, and then our second lookup is going to be 1 minus 0.025 because we need to look up on the other end of the chi-squared score, the left end, and that's going to be 0.975. Oops. Let's try that again. 0.975. So that also looks like, give me a second here, I'm getting OCD about this here. So 0.025. So 1 minus this gives me 0.975. So I'm going to look up both of these with a degrees of freedom, a DF, of 60, because that's 1 less than 61. So you go to my little table here for chi-squareds, 60. And so for 0.975, so the third column over, that's going to be 40.482. And then for 0.25, third over from the right, it's going to be 83.298. So I'm going to write that down here real quick before I forget. So this right here is going to be 83.298. And over here is going to be 40.482. Right? So now, that's not my end of it. That's just me finding the boundaries. So now my actual interval is going to be constructed. Now this one you cannot do a plus or minus with. There's no plus or minus for a standard deviation estimator because it's not really in the middle. The way you figure it out is you would do this. You would do n minus 1 times your standard deviation squared, and then divided by your critical value. In this case, the critical value of the lower end, which is 83.29. What I mean by lower end, I don't mean by small number. I mean by this corresponds to the lower end of the chart there because it's 0.025's number, whereas this corresponds with the higher end because it's a bigger tracking number, I guess you could say. So that would be your bounds there. That'd be your left-hand bounds, your lower end bounds, after you square root it, because this actually gives you an estimate for the variance, but we're not working with variance right now. So we'd actually square root this entire thing to get my left-hand boundaries. To get my right-hand boundary, is the exact same thing. It'd be 61 minus 1 times 25 all over, 25 squared, all over 40.482. And then, whoops, sorry, 482. My bad, let me try that again. Nope, no. Want some of that. 40.4, there we go, 82. Sorry, I had to rewrite that. So in this case here, we have our two setups here, and so this is a big square root over it. Now we just solve. So this top chunk here, you plug it in, you get about 21.22. And then this bottom part here, you end up getting about 30.44. So you end up with a confidence interval of 21.22 less than sigma less than 30.44. That's your best estimate for the deviation given the information in this problem here. Okay. So again, chi-squareds are a little bit tricky, but you just have to get used to them. And Again, usually people can get 90% of them done for the quiz, even if they're still a little shaky on them. But I think you guys can get it done 100%. All right, the last two here. Again, almost free of me, so just give me a little bit more time. 250 people out of 700 interviewed said that they would eat a pony burger if offered. Construct a 95% confidence interval to estimate the proportion of the population that would eat a pony burger. So, again, we're going to start with our alpha, which in this case is still 5%, so 0.05. Now, if we're estimating a population proportion, that means we're estimating a percentage, so we need to find our percentage. So p hat is going to be the 250 that said yes out of 700, right? So we run that little gambit there, we get 0.357, which is not a terrible score for um, introducing a new item into the food place. And then we need a Q hat, and a Q hat is just simply 1 minus P hat, so 1 minus 0.357, and that would lead us to have a Q hat of 0.634. And then my N is 700 because they interviewed 700 people at the very beginning of the problem. And my z-score, based on this, is going to end up being 1.96 because, like I said, that's kind of the lawyer we have in the back of the book on hand, so to speak. And then you're just going to plug into the normal E formula. So the E formula says that if you're dealing with a population proportion and a z-score, you're going to start with the z-score, obviously 1.96. I don't know why I put a 5 up there. 1.96. And then once you get 1.96 down, you're going to multiply it by the square root of p hat, which is 0.357, and then q hat, which is 0.634, all over my massive n value of 700. You multiply this through, and you end up getting a roughly decent answer, actually, of 0.035. Again, you might have some rounding after the 5, but as far as rounding up, that's as far as we can get there. And then once again, you could write this as 0.357, plus or minus 0.035. That way there's no ambiguity, and again, it gives you a little bit more time to set up stuff. So that's a little bit easier problem to write out than doing the actual, extreme intervals there. So, all right, last one here. This time we're estimating a population average again, it looks like, because we're estimating the average amount of time. It says that when we're testing the survey here, it says that they actually spent 2.5 hours on homework when 71 students were interviewed. It says the standard deviation for the amount of time spent doing the interview at all schools in the area, which is the population, because they're taking a sample of high schoolers from this school. So if we include high schoolers from all schools, that's the population. And it says that that deviation is 0.8 hours. So this is a sigma. So this is going to be a z-score problem. So first, 90% confident means that we have an alpha of 0.1. 0, or just put 0.1 there. And so we're going to have a z-score of, again, this is a z-score 1 because we're dealing with the population deviation, which it says that there is 0.8 hours. So that z-score is going to be 1.645. That's my z value. My x bar, it says here the average number they have so far is 2.5. And my sigma is 0.8 as they point in the problem. So the way I would figure out my estimate, figure out my margin of error, is if I go 1.645, my z-score, times 0.8 all over square root of my e, which is 71. Okay. Again, I don't use degrees of freedom here because it's a z-score, so I don't need to. So you multiply all this through, and you get 0.156, which, when you write out, looks like this: 25.5 plus or minus 0.156. Again, the only reason you could not do an answer like this form is if you're trying to estimate the standard deviation, in which case there is no nice form to represent the standard deviation. You just have to kind of write it out verbatim and solve it. There's no special trick with that one. So that's it for the study guide there. Again, sorry about my maybe a little bit long rambling there. I am kind of tired doing this out here, but I want to make sure I get it done and up as soon as possible. If I made a mistake here, which again, more than likely, please let me know. But hopefully I think I corrected all the ones that I made and corrected them before I published it. So as always, let me know if you have any questions. Otherwise, have a good day, night, or whenever you're watching this.